In the previous video, we have seen that we can represent a complex number as a point in the complex number plane. And the coordinates of the point z equals a plus bi are a and b. This representation is the so-called Cartesian representation, named after the French mathematician and philosopher René Descartes, whom you see here on this picture. The Cartesian representation with the coordinates a and b, the real part and the complex part of a complex number, is not the only way of representing points in the plane. Another way is the so-called polar representation, or polar coordinates. Here the point in the plane, point P, is given uniquely by r, which is its distance to the origin. R is the length of the vector from the coordinate origin O to the point P. And the second component is the angle phi, which is the gradient angle of the vector OP, which is the angle between the vector OP and the real axis. This means that a complex number set can uniquely be represented by r, which is its absolute value, and phi, the gradient angle of z. But how can we compose these two components, r and phi, to a unique expression? This is done in the following way, and this is the so-called polar representation of a complex number, which is r times e to the power of phi I, where r is the absolute value of z, which is its distance to the coordinate origin, and phi is the angle to the horizontal line, the gradient angle, and e is the famous Euler number, which is defined as a limit, as an infinite sum, 1 divided by 0, faculty of 0, plus 1 divided by faculty of 1, plus 1 divided by faculty of 2, and so on. The Euler number E is named after the famous Swiss mathematician Leonhard Euler, which you see on this picture. Unfortunately, I cannot give you the mathematical background of this representation r times e to the power of phi I, because this would require a lot of very deep mathematics, and we don't have the time to give this mathematics here. In the polar representation, r times e to the power of phi I, the angle phi is always given in radians as a multiple of pi. And angles in the southern hemisphere can be written as negative angles. It's not necessary as a negative angle, but it's possible to represent them as negative angles. So if phi is the green angle, then minus phi is the red angle, which is so to say reflected at the x-axis or the real axis. So let's look at some examples. The number 1 is always represented as 1. It's never represented in the polar coordinates. But for I, the complex number I, we have r is the absolute value of I, and the absolute value of I is 1, of course. It's the distance of I to the coordinate origin, and the angle between the x-axis and the vertical axis is 90 degrees, which is half of pi. So the number I can be written as 1 times e to the power of p half times I, or in short, e to the power of p half times I. Next number is minus 1. The absolute value of minus 1 is 1, and the angle for minus 1 is 180 degrees, which is pi. So minus 1 is 1 times e to the power of pi, or in short, e to the power of pi. The next number is minus I. So length of minus I is 1 again, and the angle is 270 degrees, which is 3/2 of pi. So minus I can be written as 1 times e to the power of 3/2 of pi I.